Hello students, last class we have studied about the chemical properties of amines. There are also some other properties, chemical properties of amines. Let us discuss. First, reaction with nitrous acid. So nitrous acid is an unstable acid. It is prepared at the time of requirement by reacting sodium nitrite with hydrochloric acid, give rise to NaCl plus nitrous acid. So the primary, secondary and tertiary amines react differently with nitrous acid. So looking at this, observing this reaction of nitrous acid with different types of amines, we can also distinguish between primary, secondary and tertiary amine. So this is also a distinguished test between primary, secondary and tertiary amine. Let us look at some example. Primary amines. So primary aliphatic amines reacts with nitrous acid at low temperature as well as at room temperature to form alcohol with evolution of nitrogen gas. Group RNH2 plus HONO. To make it simplify, I am writing HONO so that it become easier to remember. RNH2, this is a primary aliphatic amine, reacts. So divide this and this to three parts. R one part, N and H2, OH, N and so then distribute to R to this OH to nitrogen, to this hydrogen to this oxygen. So in this it gives you so that it becomes easier to remember you. ROH plus N2 plus H2O. This is alcohol. Example, ethylamine. This is a primary amine. Reacts with nitrous acid to form, so to this alkyl part OH, ethanol plus nitrogen plus water. So this nitrogen gas is produced with effervescence that can be easily detected. Primary aromatic amines react differently at different temperature. So primary aromatic amines. This is about aliphatic amine. Then primary aromatic amine such as aniline reacts with nitrous acid at ice cool temperature the reaction takes place in acid medium. Generally where we know this HNO2 is prepared by NaNO2 plus HCl. It is made acidic by adding HCl. So it gives NCl minus plus 2H2O. This is benzene diazonium chloride. This is aniline. But if the temperature is higher than 278 Kelvin, or that is 10 degrees Celsius or more than 278 Kelvin, then it gives phenol. NH2 HONO acid medium greater than 278 Kelvin, it forms phenol OH plus N2 plus H2O. This is phenol. So, aliphatic primary amine reacts at low temperature as well as at high temperature to produce alcohol with evolution of nitrogen gas. But aromatic primary amine reacts at low temperature to form a salt, but at high temperature it forms phenol. Then next come to reaction with secondary amine. Both aliphatic and aromatic secondary amine react in the same way. When the secondary amine reacts with nitrous acid, it forms nitrosamines, which are insoluble and these are yellow color liquid. Look at example. Directly I am taking your example. This is diethyl amine. It reacts with nitrous acid to form, so H and OH, it forms whole twice N, then N double bond O. This is NN diethyl nitrosamine plus H2O. This is an yellow liquid and also insoluble. Similarly, aromatic amine, that is, suppose I am taking the example of N-methyl aniline. When it is treated with nitrous acid, it forms, here also removal of water takes place. It forms N double bond O. This is N-methyl amine. Okay. N-methyl nitrosamine plus H2O. This is also yellow liquid. And this yellow substance, when bound with phenol and concentrated sulfuric acid, forms a green solution. And this green solution, when these are bound, and this green solution when treated with aqueous sodium hydroxide, it forms a blue solution. And this blue solution, when made diluted, when undergo dilution, when this blue solution undergo dilution, it forms a red solution. So, both aliphatic and aromatic amines reacts with nitrous acid to form yellow liquid. In this way, this can be distinguished for further confirmation. When this yellow liquid bound with phenol and concentrated sulfuric acid, it forms a green solution. This green solution, when made alkaline with sodium hydroxide, it forms a blue solution, and this blue solution again on dilution forms a red solution. This is called Lieberman nitroso test. Lieberman's nitroso test, and that is only given Lieberman nitroso test, and that is only given by secondary amine. Primary and tertiary amine do not respond this Lieberman nitroso test. Next come to reaction with tertiary amine. Tertiary amine. So the aliphatic tertiary amine reacts with nitrous acid to form a salt. Look at the example. This is triethyl amine reacts with nitrous acid to form NH plus one hydrogen atom by this H plus ion absorbed by this. So C2H5 whole thrice NH and NO2 minus, that is triethyl ammonium nitrite. Similarly, aromatic tertiary amine reacts with nitrous acid to form, so it does not form like this salt. Generally, it undergo electrophilic substitution reaction to form green colored para nitroso amine. Look at the example. CH3, CH3, then this is NN dimethyl aniline reacts with nitrous acid. Here also one hydrogen from here and OH from here. Liberation of water molecule takes place. Removal of water molecule. CH3, CH3, N plus H2O. This is P nitroso NN dimethyl aniline, and this color is green. Okay, so primary amine reacts with nitrous acid to form alcohol with evolution of nitrogen gas at low temperature as well as high temperature. Primary aromatic amines reacts differently with nitrous acid at different temperature. At low temperature, at ice cold temperature, it forms a salt, aryl diazonium salt or benzene diazonium salt, and at high temperature, it forms phenol. Secondary amines, both aliphatic and aromatic, react in the same way with nitrous acid. They form yellow liquid, which also undergo Lieberman nitroso reaction. Tertiary amines, aliphatic and aromatic, react differently with nitrous acid. So the tertiary aliphatic amine formed a salt, and the tertiary aromatic amine formed para-nitroso amine, which is green in color. It undergo electrophilic substitution reaction. In this way, nitrous acid is helpful to distinguish between primary, secondary, tertiary amine in aliphatic as well as in aromatic amines. It is also helpful to distinguish between primary aliphatic amine, primary aliphatic and aromatic amine, tertiary aliphatic and tertiary aromatic amine. This is also helpful to distinguish between primary, secondary, tertiary aliphatic amines. First case, it gives nitrogen gas. Second case, it gives yellow liquid. And third case, it gives a salt. Next come to another reaction, that is a reaction with Hinsberg's reagent. Benzene sulfonyl, Hinsberg reagent is benzene sulfonyl chloride. So in this test, the amines are treated with benzene sulfonyl chloride. These are taken with benzene sulfonyl chloride in presence of aqueous potassium hydroxide. So benzene sulfonyl chloride, then aqueous potassium hydroxide solution. The primary, secondary, tertiary amines, they reacts different way with this Hinsberg reagent. In this way, this is used to distinguish between primary, secondary and tertiary amines. The primary, second, tertiary amines react differently with Hinsberg reagent in presence of aqueous KOH. So in this way, this can be distinguished. The primary, secondary, tertiary amine can be distinguished. So this primary amine, when treated with Hinsberg reagent, then with aqueous potassium hydroxide. So first, these are soluble. So this is soluble in KOH, which on acidification becomes insoluble, forms precipitate. Insoluble on acidification. First treated with benzene sulfonyl chloride and potassium hydroxide. So this is soluble in KOH and insoluble on acidification. Alkaline medium soluble, acidic medium insoluble. Secondary amine. So when treated with benzene sulfonyl chloride and aqueous KOH, it is insoluble. Insoluble in alkali medium as well as insoluble in acid medium. Insoluble on acidification. And tertiary amine do not react with Hinsberg reagent. Tertiary amines do not react with Hinsberg reagent, hence remain insoluble in potassium hydroxide but soluble on acidification. So due to formation of salt. Primary, soluble in alkali medium, insoluble in acid medium. Secondary, insoluble in alkali medium as well as acid medium. And tertiary amines, insoluble in alkali medium but soluble on acidification. So observing this, the primary, secondary and tertiary amine can be distinguished. Look at the reaction. So this is benzene sulfonyl chloride reacts with primary amine. This is primary amine. So first it forms NHR here minus HCl. Okay, so this product is formed, and this product when treated with aqueous KOH, it forms a salt. N minus so this forms sulfonamide. This is N-alkyl benzene sulfonamide. So this is a salt of N-alkyl benzene sulfonamide. So which on acidification, if treated with, it forms again this compound which is insoluble, NHR. This is N-alkyl benzene sulfonamide. This is N-alkyl benzene sulfonamide. So this is insoluble in acid medium. This is soluble in alkaline medium. This one soluble. And this one insoluble. So this one insoluble, this one soluble. This is primary amine. It forms N-alkyl benzene sulfonamide. N-alkyl benzene sulfonamide. Similarly, when we consider about secondary amine, if we consider about secondary amine, here also and treated with KOH, here minus HCl also there. It forms NRR, NN dialkyl benzene sulfonamide, NN dialkyl benzene sulfonamide. This is insoluble plus 2 KCl plus KCl plus H2O. This is insoluble in alkaline medium as well as insoluble on acidification. Similarly, if we consider about tertiary amine, then tertiary amine do not react. Tertiary amine do not react with benzene sulfonyl chloride. No reaction. So when treated with KOH, this is, suppose I am writing here like this, potassium hydroxide first is treated and made alkaline. So when it made alkaline, then no reaction. In this way, this is insoluble. But when this is treated with HCl, this amine reacts with HCl to form salt. R3NH plus Cl minus, that is trialkyl ammonium chloride. Trialkyl ammonium chloride. So in this way, primary, secondary and tertiary amines react different way with benzene sulfonyl chloride. So primary amine form N-alkyl benzene sulfonamide, which is soluble in alkaline medium, insoluble in acid medium. Secondary amine forms NN dialkyl benzene sulfonamide, which is insoluble in potassium hydroxide as well as on acid medium. And tertiary amine do not react with benzene sulfonamide. It forms insoluble with potassium hydroxide, insoluble compound with potassium hydroxide, insoluble or precipitate with potassium hydroxide, and this is soluble in on acidification. In this way, primary, secondary and tertiary amine can be distinguished. So aliphatic and aromatic amines, some reactions are there. Aliphatic and aromatic amines reacts in the same way. But there is some special reactions for aromatic amines. That is electrophilic substitution reaction of aniline. The simple aromatic amine is aniline, so here we are considering about aniline. So you know aniline has NH2. There is a lone pair of electron on nitrogen atom. When the lone pair of electron is conjugation with double bond, then it come into resonance. So due to resonance, these ortho and para positions become more electron rich. That's electron density. In this, the electrophilic substitution reaction takes place at ortho and para position. Already we have discussed what is the relative structures of aniline. So this NH2 group is ortho-para directing in nature as well as ring activating. So it activates the ortho and para position so strongly so that when electrophilic substitution takes place, all the ortho and para product are substituted. The finding monosubstitute product is actually difficult. For example, if we consider about halogenation. So when aniline treated with bromine, it forms 2,4,6 tribromoaniline. When aniline treated with bromine water, it forms so 2,4,6 tribromoaniline. It forms 2,4,6 tribromoaniline because this NH2 group is ring activating in nature. So it activates the ortho and para position strongly, so strongly that the tri-substituted product is formed. So it cannot stop this reaction by monosubstituted product. But if, however, it is necessary, sometime it is necessary to find the monosubstituted product. In that time, what is carried out here in this NH2 group? This NH2 group is protected by acylation. If this NH2 group is protected by acylation, then the reactivity of the activating nature of this NH2 group decreases. The ring activity nature of NH2 group decreases due to presence of the CO group, carbonyl group. So monosubstitution product can be possible. So when simply aniline reacts with bromine water, it forms 2,4,6 tribromoaniline. But if we want to prepare monosubstituted product, then we have to first protect this group. Look here. But when first aniline treated with acetic anhydride in presence of sodium acetate, generally it undergoes acylation. Already we know this reaction. It forms NHCOCH3. So here we can write minus acetic acid. So this is acetanilide. And if this is treated with, and now if this is treated with bromine, then it forms mixture of NHCOCH3Br plus NHCOCH3Br. It forms mixture of ortho and para bromo acetanilide. And after getting this ortho and para bromo acetanilide, this is the major product, more amount of para, and this is the minor product, less amount of ortho product. And when these are undergo hydrolysis H2O in acid medium, then we can regain this aniline as NHBr plus Br. So here we get aniline. So aniline, to get this mono substituted product, first aniline is treated with acetic anhydride to form acetanilide. Then after that, this acetanilide treated with bromine to form a mixture of orthobromo acetanilide and para-bromo acetanilide. And these when undergo hydrolysis, so this acetyl group is again removed and it forms orthobromo aniline and para-bromo aniline. It is your orthobromo aniline and this orthobromo aniline, and this one your para-bromo aniline. Okay. Similarly, next come to nitration. Nitration. When aniline, so you know this is orthopara directing nature. You know aniline and nitrating mixture is concentrated sulfuric acid and concentrated nitric acid. When we take the mixture of concentrated nitric acid and concentrated sulfuric acid. When you take the mixture of concentrated nitric acid and concentrated sulfuric acid, this should give your ortho and para product. But what happens? This NH2 group is ortho para directing, okay. And again this NH2 reacts with this acid to form anilinium ion, NH3 plus ion. And this anilinium ion is now not orthopara directing, this is meta directing. So in this way, aniline when treated with concentrated aniline when treated with concentrated nitric acid and concentrated sulfuric acid, mixture of this nitric acid and sulfuric acid, it forms a mixture of meta-nitroaniline and para-nitroaniline and a less amount of orthonitroaniline. So actually when this is treated, it gives NH2, NO2, this is para-nitroaniline plus NH2, NO2, M-nitroaniline plus NH2, NO2, O-nitro, ortho-nitroaniline. This is about 51%, this is about 47%, and this is only about 2%. So when aniline treated with, it gives a mixture of this. But if this group is protected, by acylation and then this nitration carried out, it forms a mixture of para-nitroaniline and orthonitroaniline. Look at the equation. NH2 first, acetic anhydride minus acetic acid give rise to NHCOCH3, then treated with concentrated nitric acid and concentrated sulfuric acid give rise to NHCOCH3 NO2 plus NHCOCH3 NO2, para-nitroacetanilide, and this is acetanilide. This is p-nitroacetanilide, and this is O-acetanilide. And this on acidification, on hydrolysis, acidic hydrolysis forms para-nitroaniline and orthonitroaniline. But the para product is more than ortho product. Okay, this is about nitration. Then come to sulfonation. So aniline reacts with concentrated sulfuric acid to form sulfanilic acid. That is NH2 plus concentrated sulfuric acid. Actually first it forms a salt. This is a base, this is acid. So it forms salt NH3 plus HSO4 minus. So monobasic acid, suppose this is a monobasic acid, one hydrogen can be replaced. This is a dibasic acid, but it gives two series of reaction, one by replacing one hydrogen and another time replacing another hydrogen. So here only one hydrogen is replaced, NH3 plus HSO4 minus, which when heated, if this is heated above 450 Kelvin, then it forms, so minus water is there, so it forms NH2, this is para-amino benzene sulfonic acid. Para-amino, so this is sulfonic is the main functional group. Now this becomes the substituent para position, para-amino benzene sulfonic acid. So this para-amino benzene sulfonic acid, it exists as, so this is acid, it can give H plus ion, and this is the basic part, it can receive H plus ion. So in this way it forms NH3 plus SO3 minus. So this para-amino benzene sulfonic acid exists as a zwitter ion structure. para-aminobenzene sulfonic acid, it has a deuterion structure. Okay, so aniline reacts with concentrated sulfuric acid. First it forms a salt which on heating forms para-aminobenzene sulfonic acid, also called sulfanilic acid. And this sulfanilic acid exists as a deuterion structure. Next, this aniline do not undergo Friedel-Crafts reaction. So why it do not undergo Friedel-Crafts reaction? Because this aniline has NH2 group, this is acidic group, and when the Friedel-Crafts reaction takes place in presence of Lewis acid, either anhydrous aluminum chloride or ferric chloride, so this aniline form salts or compounds with this Lewis acids. So this is a Lewis base, it forms salt with Lewis acids. It reacts with this Lewis acids. In this way, it do not undergo Friedel-Crafts alkylation and acylation. Okay.